Hey guys, we get to do a test run on how this is going to look like when I am on maternity leave. I am out today with a sick child, so I wanted to continue doing notes and a little bit shorter than what I wanted to get to today, but still wanted to at least continue on moving through the material. We are looking at rate law today, specifically going to be looking at differential. So at the end of the day on Friday, I told you there were two different types of rate laws that we use. The first one is differential rate law. This is usually when you're asked for rate law or a rate law expression on an AP exam. This is what they're referring to as a differential rate law, which looks like this, which we'll talk about in just a moment. This is done, or the data that's given with this is multiple trials. And all we're looking at is how changing concentration affects initial rate. So this is not what we were looking at on Friday, where we were letting the reaction just kind of go and watching how the rate changed as the reaction progressed. This, we're just letting the reaction go for a very short time period, measuring the rate at that time period, and then trying it again with different concentration values to kind of see how the concentrations affect stuff. This is going to be becoming important when we talk about mechanisms, because this does give us very viable data about collision model and what two species or multiple species have to collide for this reaction to occur. Because unfortunately, it's not always what the reaction is. So this reaction is A plus B, so we might make the assumption A must collide with B. However, that's not always the case, and that's where reaction mechanisms, which we'll talk about a little bit later this week, come into play. So don't stress about that right now. Right now, I just want you to focus on what differential means. We then have integrated data. Integrated data is what we looked at on Friday, which is this guy right here, where we just kind of let the reaction run and saw a concentration change over time. So this is a one trial type thing, and we're looking at how time affects concentration and how those concentrations affect rate. So if I was to look at the different types of data I might be given, so this is my reaction. This type of data, notice here, I've got concentration and how it's changing versus time. This is integrated data. Versus over here is differential data, which off to the side, there should be experiment 1 and experiment 2 here, and it's just not written. I might start with 0.9 molar and calculate my initial rate or measure my initial rate, and then half that molarity and see what happens to my rate. Both of these are very common. Somebody on Friday asked which one's better. There's not one that's better. They give us different sets of data, and I can go back and forth between each of them to get my rate law. Very commonly, integrated data is looking at one species in a chemical equation versus our differential allows us to look at multiple species. And then from there, again, I can translate these back and forth into each other. So both of them are necessary, both of them are good, and both of them just give us different pieces of data that are important throughout this process. So what I want to focus on just today is this differential data, and then have you work through some problems on your own. First thing we need to talk about is what in the world is a rate law? A rate law or rate law expression is really just an equation. The equation is based off of the reactants alone. So we're only looking at, again, this initial aspect. So there are no products at this point in time. There are just reactants. And we're just focusing on how the reactants are colliding. So no equilibriums involved here. Concentration hasn't decreased dramatically. We're just talking about that very beginning onset of the reaction. And it's written based off just the concentration of the reactant. So if we look at this reaction, we have A plus B going to D and C. Our rate law would simply be rate equals K. K is a constant value we will be using a lot this semester. And what I do want you to recognize is this is lowercase k. A lot of our other K's will be capitalized K. Our equilibrium K's are capitalized K. Our rate laws are lowercase k's. So that's kind of just a constant value. That value will depend on the reaction. It will depend on the temperature. There's a whole lot of factors that go involved in this, but we just call it K, because C is too common in science to be a variable. So K is what we use for constant. We then put brackets, remember this means molarity, around each of our reactants, and we raise it to a value. This value is called an order. It is not called a power anymore per se. It is called an order, and we can see any type of order throughout this process as long as it is a positive value. We won't see negative values, but we can see fractions, we can see 0, we can see 1, 2, and 3, which 1, 2, and 3 are the more commons. You're not going to typically see 4 and 5, though they're not out of the possibility. They're very uncommon because of what they represent, which we'll talk about when we get to mechanisms. But fractions and positive values between 0 and 10 even are not out of the question here. The big thing I want you to recognize is that these values, these orders, N and M, do not come from the coefficients of the balanced chemical equation. They actually come from that differential data, or even the integrated data can allow us to calculate them too, but it is easier to typically get them from the differential data. So let's look at some differential data. Okay, actually, sorry, missed a slide. Let's talk about the rate laws. First and foremost, just like I already said, products do not appear in this, and that's because we're trying to look at just at initial onset. There's no products formed yet, and we don't want the reverse reaction affecting our rate, because remember, some reactions, when they produce products, those products can go back and form reactants and form equilibrium, and then all sorts of things come crazy here. So we're just trying to kind of isolate just the reactant aspect here. We then have the exponents, or the powers, or the orders, and I will call them orders because that's what they are considered in this case, cannot be written from the balanced chemical equation, meaning they must be determined experimentally. They cannot be written from the coefficients. So what does all that mean? What that means is this. Here's a sample set of data, and we have our balanced chemical equation. Okay, and if I asked you to write the rate law, what that would look like is simply, it would be rate equals lowercase k, brackets around NH4 plus raised to the x is what we'll call it, brackets NO2 minus, and we'll call that y. Now, we're not technically done. We actually have to figure out what is x and what is y. It's not enough just to write the rate law. So this is kind of our basic rate law. Now we have to use this data to determine what those values actually are. And the way we do that is we look at it from a comparison perspective. So what I mean by that is we're going to go down here and look at our data. Okay, and what we want is we want to find two experiments where one species is being held constant, which sometimes works and sometimes doesn't, and another species is changing. So if I'm looking at experiment 2 and 3, my ammonium is staying at 0.1, but my nitrite ion is going from 0.005 to 0.01. Now we have to think about, okay, well, what is this relationship? Okay, and this relationship, and I apologize, this thing is not calibrated very well. Nope. Okay. Anyways, I can't write on here very well. The relationship is 2, so we're doubling these. Now we go over here and we look at our rate. Well, what happened to our rate? We went from 1.35 to 2.7. Hopefully we can kind of see those numbers and realize what's happening here, but sometimes you can use a calculator to figure it out. But if we look at this, we're doubling rate as well. So what does that mean? If we double concentration and we double rate, what that actually means is mathematically our order is 1. So what I want you to kind of think about here is if I was to think about it this way. There we go, sorry. 2 to the x equals 2. Well, what is x? X must be 1. So that means when I'm writing my rate law, so rate equals k, I still don't know what NH4 is because I haven't looked at that, but I now know NO2, the way it changed, is to the power of 1. Now we're going to go do the same thing with the NH4. So we're going to look at these two experiments. Here, concentration staying constant, but here, my concentration is doubling. And if we jump over here and look at what's going on, Okay, so if we were to actually look at these numbers, we go from 0.01 to 0.01, so there's no change happening to NO2, which means if there's a change of rate, it's not due to this guy, it's due to this guy, which is going to allow us to determine our order for NH4. So we go from 0.1 to 0.2, which if this thing will let me write on it, it's a little high. There we go, that's twice as big, so we're doubling our concentration. Now we come over to rate and look at these same two values, and again, I apologize that this thing's being a little bit wonky. There we go, close enough. If we were to look at these, it's actually a quadruple factor. In other words, going from 2.7 to 1.08 times 10 to the negative 6 versus 10 to the negative 7, I'm actually quadrupling my rate. So doubling concentration is quadrupling rate. What does that actually mean? Well, if I come back up here, 2 to the x equals 4, x must be 2. So that means my order for my NH4, which that's too low, there we go, is 2. So my actual rate law here, if I'm going to go down and clean this up just a little bit, would be rate equals K, NH4 to the second order, so what we call that, or order of 2, and NO2 minus to the order of 1. So let's look at one more before I let you loose to work on your own. Okay, so we've got this reaction, and in here we have 3 different species changing. And actually what I'm going to do is I'm going to pause, stop this video because I'm running out of time, and then, because I only get 15 minutes per video, guys, I will do another short video going over this data and then how we answer some of these questions, and then we'll go from there.